The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
As we come close to Thanksgiving, we have shrinkage here. People probably already left home. Hopefully everybody who left home finished their report. So you guys have all looked into how to do the final project and you have all the ideas how to go and optimize. How many people have like downloaded, compiled and ran and you know what's going on? Okay, good. And yeah, exactly, yeah. Okay, it's happening right now, okay, good. But so I will repeat this what I said last time in here. We are going to have a design review with your masters. So you just look for us to send you the information. That means we need to come back from Thanksgiving, schedule it early so they can help if you have any changes in design process. And then we have a competition on December 9th in class here, trying to figure out who has the fastest ray tracer created. And then in fact, this year, there's Akamai prize for the winning team, including they are going to have a celebration and demonstration in their headquarters. You get to go get a tour with their NOC and stuff like that. Plus, every winning member is going to get iPod Nano. So there's a lot more motivation now to get the fastest running ray tracer. Okay, so with that, let's switch gears a little bit. So today I'm going to talk about distributed systems. So till now what we looked at was, okay, given a box, how to get something running as fast as possible inside that box. And today we are going to look at going out of the box, outside the box. Basically, we want to scale up to clusters of machines. That means in a room, you can have 10, 15 machines. In fact, for your class, you guys are using, how many machines do we have? 16 machines. So you're doing independently, but you can use it as a one gigantic machine if you can, and run something. And data center scale. This is kind of people like Google and Amazon has these kind of things. And finally, planet scale. If you want to run something even bigger, larger, what do you have to deal with and what kind of issues you have to deal with? Oh, this is trying to reboot my machine and I have to be pressing this button probably 4 or 5 times during the day. Okay. So cluster scale. So you want to run program on multiple machines. And okay, let me put it that. Why the heck do you want to do that? I mean, what's the advantages of having, instead of running on one nice machine, running on a cluster of machines? What do you get? What? It's cheaper, that's a good one. It's cheaper to get a bunch of small machines than to buy a Himango mainframe type large machine. Yes, that's a very good answer. What else?
It's very slow. It's slower.
So you want to run something because it's slower? Yes, so there's some trade-off between speed, but it might not be that much. I mean, even when you get a gigantic machine, there are bottlenecks in it. In a cluster kind of thing, you can avoid the bottlenecks. But hopefully, you're trying to do it to get some performance in scaling to large number of users and whatnot. So basically, what you want to get is get more parallelism, because now we have more machines, more cores, and hopefully get higher throughput, definitely, because you have anything. Hopefully it's a little bit of lower latency too, because if you have one gigantic system, if everything has to go through bottlenecks, it might be slower than basically having different systems. So assume, just get an example, if you are something like Verizon, trying to do Netflix, trying to serve you videos. Okay, it makes much more sense to have a bunch of clusters of machine, each kind of doing a lot of independent work, than trying to send all the videos through one machine. Another interesting fact is robustness. So till now, you guys didn't care about robustness because something went wrong. The entire thing collapsed. I mean, there's no half-baked machine. Did the machine crash? Your program crashed, everything died, so you just kind of have this fatalistic attitude. Okay, if it crashed, everything is dead, so why bother? But in these clusters, if you have a lot of machines, if one machine dies, there's many other things to pick up. So you can have a system that probably has availability much higher than what you can get on a single machine. And finally, cost savings, because it's cheaper to do this. Have a bunch of small machines, and places like Google has really taken advantage of that. And so there are issues we have to deal with. Now we have to program this damn thing, and if you want to get performance, you need to actually program in a way to get good performance. You don't want to run much slower and less performance than one box. You want to get performance and also performance scalability. That means if you get 10 machines, you want to get some performance. If you have 20, hopefully you want to get a lot more performance in 20. So how do we keep things scaling in there? And also other thing is robustness. So the idea there is if you have one machine, you are fatalistic. If the machine goes, everything goes, you don't care. But if you have a lot more machines, you want to make sure the application runs even a machine failure. Worse, if you have a lot of machines, there are a lot more chance of failure. So if one goes down, everything crashes still, then your application will be a lot less robust even than a single machine because there are too many moving parts to go wrong. So you want to actually deal with this robustness, so that adds a complete new dimension in there. We are not going to go too much deep into robustness, but that is one big thing that you have to really worry about when you go to distributed systems. So okay, what's a distributed system? So this is what I have been working we have been working so far. I think this, can see if they can reduce the lights. From up, I guess up there you can't, okay. Please, we don't go fully dark, we'll see. All dim. Oh, that's you guys. Oh well, okay. So don't go to sleep, even though light is in there. So this should be the other way around. I don't have any ways to darken this side. So these are the machines we have been thinking about. We have a memory system, and more than just having a shared memory, we have cache coherence. So that means if two people want to communicate, to write to this single memory location, and voila, that data appears all over on all the different cores. So we can use that information to basically communicate through the process. That's really nice. So a distributed memory machine has no shared memory. So each memory is different. Now how are we going to communicate? Message pass. So yeah, this is not sufficient. We actually need something additional, something like a network or Ethernet or something behind sitting out there actually let you communicate between each other. So if you just really look at the kind of cost, this is a back of the envelope type calculation. Register is probably 1 cycle, cache is about 10 cycles. If you go to DRAM, you can get about 1,000 cycles. Remote memory going somewhere across is again another like order of magnitude off from that. So of course you keep adding, and that's probably the reason that sometimes things can be slower, because now we have another layer that's even slower. So we have to think about it, worry about it when you're writing code for these type of machines. So in shared memory machines, we learn in languages like Silk, it's very nice to communicate because we synchronize via locks and all communication via memory. Because when you write something, if you look at that memory location, everybody else will see it, and if you put the right synchronization, hopefully you'll get the value you want. In message passing distributed memory machines, there's nothing like that. So what you have to say is you explicitly send some data across. So you have what we call messages. And that means if you want to send something to the other, if another processor needs to look at something, you have to send it to that person. So you have to originate yourself saying, I'm sending that, other person has to receive it, and they have to put it wherever you want. So everybody's address space is separate. And if you want to synchronize, you have to also do it to the message. So you send a message, and other person wait for the message to come. And so this kind of shows you what normally happens in messages. See, in a shared memory, there's nothing called message size. You write a cache line, the cache line moves. And you can't keep changing the cache line size. Hopefully prefetcher will be good and do something nice, but you don't have that much choice. In messages, you can compose any size of message you want. So what this graph shows is kind of the minimum cost and average cost of different size messages. So there are a couple of things to get out of this graph. One is that if the message is even 0 length or very small, you still have overhead. You have to send the darn message. So even if you say nothing, okay, it costs you some amount. And the second thing is, as the message gets bigger and bigger, the cost keep increasing because now you are sending more and more data. So if you want to really amortize the overhead cost, you have to send large messages in there. The other thing this chart shows is that as messages become bigger, the kind of the distribution of overhead is all over the map. Because now you're sending large things, a lot of other craziness happens to these things, so sometimes it can go fast, sometimes it can be pretty slow. I will get why it might be sometimes this kind of distribution shortly. So the main point is that you don't want to send smaller messages if you can, because the overhead is too high. So why is this? Why is sending messages complicated? Till now, there's nobody sitting between you and hardware. Okay, once you send the program run, you own the entire hardware, and after figuring out all the weirdnesses on x86, there's nothing in between. You probably won't look at the compile code. If you look at what assemblies generate, you have full view what's going on in here. Unfortunately, message passing, a lot of other things come into play. So if you want to send a message in the application, say, aha, I'm sending a message. And normally, it will do a system called operating system. And normally, this message will get copied into the operating system. There's a copy in here. There's operating system call here. Operating system wakes up. This might even deschedule. There's a lot of things going on. And then the operating system has to send it to the network interface card. And the network will say, OK, oh, I can't send long messages. I'm going to break into a bunch of small messages and put some hardware here. And it will end up in the other side. In bunch of fragmented small pieces that the network interface unit has reassembled into one message and deliver up. And this will probably copy back into the application. So what that means is there are a lot of other things getting involved, each optimized separately, each doing a lot of different things. And so that is why you have this big unpredictable mess happening in message passing. And so there you not only have to worry about your code, you have to worry about what the operating system is doing. You have to worry about what the network is doing. You have to worry about your network cards doing. So there's a lot of moving parts in here. So if you want to get really, really good performance, people have to kind of worry about all these things in here. So let's look at kind of how a message works. So I hope you can see this diagram. Can you see this? Barely. So let me say, so I have a sending process and a receiving process. Oh, don't reboot, please. Okay. And so what happens if this is a message, if we are sending without any buffering of a message, that means I am not copying it anywhere. So assume I want to send a message. I said, oops, I have a message to send. And then what happens in this model is, okay, until the receiver is ready, you have to wait. Because there's no place to send the message. So when finally when the other side say, okay, I want to receive something, it will send this, tell this guy it's okay to send. And it will copy the data, and then after the copying the data, both part can continue. So this is what happens if sender want to send early. If you are very lucky, minute you try to send, the receiver says I want it, and you have very little delay and everything get copied, and that's in your lucky case. The other case is the receiver wants some data, and then, but the sender is not ready, so your receiver has to wait until the sender wants to send it. And when it's ready to send, you copy the data in here. So this is kind of a very naive, simple way. What can you eliminate out of this? How can you make it a little bit faster? Yeah, okay. If you buffer, what will eliminate? What will go away? Out of, we have this overhead, and this overhead. Which overheads can get eliminated? Wait for send can go ahead, okay? So what happens is, so here actually what you're showing is buffering also with some hardware support. That means I am trying to send something, and a minute I copied it out there, I can keep working in there, and somebody in the background will send the data. It will arrive here, and then if it wants it, the data is there. Of course, if the receiver comes early and asks for data, you can't do that. Still, you have to wait because the data is not there. However, if there's no hardware support, both has to probably wait a little bit because you have to get the data copied. So if you have a lot of hardware support, you don't see this copy time. But if there's no hardware support, you see some copy time going in here. So what's the advantage of this versus, okay, tell me one advantage of this method versus this method. So of course, this one is, there's a lot of wait time and stuff like that. We know that. But is there any advantage of doing this one? Just waiting until sending and sending it there versus this kind of a nice sending it in the background? Synchronize is one advantage. What else might happen? So what else you have to do to get this kind of thing working? So in order for this to make progress, what do you have to do to data? It has to copy. So it has to get multiple copies. So from application space, you have to get copied to operating system space. It has to get copied into the networking stack. So data keep getting copying and copying and copying in there. And in here, you basically don't copy. You just say, okay, wait, I'll keep the data. And when you're ready, I will send it directly in here. And you can directly probably even send it to the network layer and send it. So if you send in a lot of data, this copy might overwhelm you. So this might even be better if you're sending like huge amount of data. So that's one advantage of having a system like that. And of course, hardware, so if there's no hardware support, you have to basically, still you have to do some copying in here. So, so this is, what am I showing here? So what we are showing in here is non-blocking. So one way to look at that is when you're sending, when you say request for send, what you can say is, okay, I continue, but I haven't copied the data. I have my data in here, but I'm doing that. What I will tell you is like, okay, look, this data still haven't moved out of my space yet. So I have to worry, I can't rewrite the data. And at some point, when you say I want the data, it will go there and bring the data for you and continue like that. So between this time, since I don't want to make too many copies, I have to make sure that I don't touch that data. Or I have to copy it. So that's my question here. And of course, if you have no hardware support, you have to actually put some time into actually doing the copy. So this is nice. So, but we want to have a little bit of a high-level support to do this. So this is not as nice as things language like Sail, because you have to now worry about a lot of other interesting things going on. So what people have developed is this called MPI language, message parsing interface language. It is kind of a little bit ugly, but that's the best people have these days. A machine independent way of when you have the distributed systems to communicate with each other. So, oops, that's not good, my phone. Sorry about that. So what happens is each machine has its own process. So it's its own memory. So there's no shared memory or anything like that. Its own thread of control it runs. And each process communicates via messages. And data is sent as is needed. And that means, but you can't send things like pointers because there's no nation of pointers. You have to actually have a data structure that's self-contained, sent to the other side. So here's a small program that I'm going to kind of walk through that. So I have main, and I'm setting up a bunch of these variables. For now, those are not that important, but for completeness, I have that. And then, of course, if you use something like MPI, you have a bunch of setup things that you have to do. So basically, I cut and pasted with what people normally have to do in setup. And then, I have this piece of code. This piece of code, what it does is this same program runs on multiple different machines. Okay, so everybody runs the same program. But then at some point, I want to know in my machine what to do. So what I do is I check who am I. Say, am I machine 0? If I'm machine 0, do this. If I'm machine 1, do this. So by doing that, I can write a piece of code that everybody runs, and everybody figures out who they are, and if they are the given thing, what to do. So here what it says is, okay, if I'm machine 0, my source and destination is machine 1. If I'm machine 1, my source and destination is machine 0. So I'm trying to communicate between each other. So if you look at what happens is first, I am sending basically to this machine. So I'm sending something into this machine. So the syntax, I'm not going to go through that. You don't have to know that, but what you need to know is that I'm trying to send something. I tell explicitly who to send. And there has to be a matching receive in the other end. Otherwise, sends goes somewhere and it goes bad. Send, yeah, you can send it, it can probably go bad, but receive, you have to have somebody who sends for that. So the receive basically has to have matching, and then you send it that direction. And then what I do is I receive in here, and this guy sends me in here. So question, I did send receive here. What happened if I did also send receive here? If I reorganize these two, what would happen? If I use the same piece of code, that two pieces of code, then I don't even have to make this two separate code. I can basically factor this out down here. I do a send receive here, and just set the IDs. What happened? Sure. These things are what you call blocking sends. If you are blocking sends means until receiver receives, it might be blocked. If you are doing a blocking send, okay, that means if two guys are trying to send, nobody's receiving. You have what? You have deadlock. So that's why I actually had to do this thing. This is blocking send. So instead of blocking sends, so of course there's some finalized things. I had to do that at the end. I can do this one. What this says is, okay, this is actually even a little bit more complicated. What I am doing is I have a bunch of buffers here. I have how many processes? I have a bunch of buffers in here. I have, I guess, my ID number of processors, no, numtask number of processors. What I am sending is I am sending a circular buffer. I am sending around to everybody. Both direction. So I am sending the previous and next. So assume something is sitting numtask things, I am sending back and forth. So here what I am doing is these are basically non-blocking sends and receives. So first I am issuing a receive. So even if I receive, it says I have intent to receive, but I am not receiving something, I am not waiting. So I can continue. And then I am doing the send. So otherwise if I just do receive and send, if it is blocking, it's going to be deadlocked. But here I do that. And then in this wait for all, what it says is, okay, now I issued a receive. Now wait until that receive is done. So before I use the data, I have to wait for all in there. And also when I do the send, I am wait for all in here. So why do you think it might be advantageous to do non-blocking receives and non-blocking send? So sends, it makes perfect sense, because once I have sent, I want to continue because I don't have to wait for anything. I'm done. So blocking sends is not that useful. But how, receives, why do you want to do non-blocking receives than a blocking receive? Because when you want to receive, you have to wait till the data comes to do anything, because that's what. But non-blocking receives means I have to receive early and then wait for the receive to happen at this point. What might be advantage of doing a non-blocking receive? Anybody can think of advantage? It's harder. Now you have to remove the receives from the synchronization point instead of writing one receive.
When I receive from my multiple machines, so then you can receive whenever.
That might be one interesting thing, because you are expecting multiple receives. You don't know what's coming first. If you do non-blocking receive, then you can be opt out to the first receive to arrive and then basically work on. That's a very good point. Okay, what else? What other things what other advantages you might have having a non-blocking receive? Receive fails. Okay, receive fails here, that's complicated. But another interesting thing might be space. Because when I receive the non-blocking receive, I know where the data has to be. So I have already allocated the buffer for that. So if the data comes now, I can directly copy into my local buffer if there's already a received issued and a space allocated. Normally, other way around, until you issue the receive, you don't know where the data has to be, so they has to get copied at that point. So here you can keep a buffer, and hopefully, if you're lucky, the send haven't happened yet. So you issue receive, set up the buffer, and when the data comes, you say, here's the matching receive. Directly put it there, bypass any copying in the middle. So that's the advantage here. So in here, I did a wait for the receives here, did the work that uses the data, and wait for sends here afterwards. Okay, could I have moved wait for sends before the work? What happens if I have moved wait for sends before the work? Is it incorrect? How would people think this is incorrect? Is it incorrect to move this wait for sends, all the sends before the work? So you move this item above. Because work is where all the work happens, I assume that uses this data. So if wait for sends above, what happens? Yeah, you lose. You're waiting for something that you don't have to wait. Of course, you can't move this down because that means you might start using and trying to use data that's not there. So this has to be here. And this, basically, for performance purposes, has to be afterwards. So of course, you have to worry about a lot of correctness issues. One is deadlocks. So there are two types of deadlocks. That's blocking sends and receives that we talked about. But there's also other types of deadlocks that happen because of resources. So let me get to that in the next slide. And the other interesting thing that can happen is stale data. In your shared memory machine, you need to update the data. You know everybody's going to see that because hardware takes care of that. But in a message passing machine, it's up to you to get the latest data when it's needed. So if you don't get the latest data, you think, I have the data, but it might not be the right value because you haven't gotten something new. So it's up to you to basically send the data out in that. And also robustness is a big issue because the fact that you have multiple machines means you can make it robust, but the other flip side is it's up to you to make it robust. So that means you have to figure out if a machine fails, how to respond to that. So if you're all waiting for a machine data to come, it fails. Okay, there are a lot of issues about my timeout, and then you have to go and deal with that. So that can make the programming a lot more complicated. And if you just don't do that, your overall program will be a lot less robust than a single machine because there could be a lot more failures in the large system. So here's some kind of deadlock that can happen. What I am doing is processor 0 is sending and processor 1 is sending data to each other. It doesn't have a real read-write deadlock because I am first sending, and then I am receiving. So this sends here, and this receives from here, this sends here, and then receive. So normally it looks like I'm sending two things. It should go, and I am receiving that. But assuming that I'm sending huge amount of data. Okay, so I start sending, and then other doesn't have enough room to receive. It just say, okay, I don't have any room to receive. I have to wait until the data, at least the data start getting consumed to start receiving. Okay, if you keep sending multiple of send, assume I do multiple of send, more than one, multiple of sends here, I might get deadlocked. I might get blocked because other guy haven't received the receive, and he's also trying to send multiple things. I might get blocked in here. So I might get into this crisscross situation. If we were trying to send something, but other guy can't proceed up to get the receive. So even though if program looked like there's a nice matching send and receive, there are no cycles. There's a cycle created by the resource usage in here. So if you are doing lot of sends before lot of receives and vice versa, you have to be careful. If you do too much of that, it's nice to block things, move things up, but if you have too many things, then you might end up in a deadlock situation, even though traditionally it might not happen. So you have a host of other performance issues that you have to deal with. So let me address a couple of them and what it might shows up. So one big thing is occupancy cost. Because when you do shared memory, minute you basically issue instruction goes, executes, you are done with that, and that operation is finished. When you are doing message passing, each message is very expensive. It has to do a lot of things. You have to do a context switch, do a buffer copy, and a network protocol stack processing, and then might have to do another context switch for that. And there's a lot of this copying and stuff happening. And the network controller might interrupt the operating system to say that there's data coming, copy the data in there, and you send a signal to application. So there's this huge amount of things happen just for one message. If you are sending like one lousy byte or one even like kilobyte, it just do a lot of millions of instructions just on behalf of small amount of data. So there's a large amount of cost associated with that, the overhead in there. So setup overhead is very high, and so what you want to do is you want to amortize the cost by sending large messages. So what you want to say is like, hey, look, I'm not sending this small thing. I am going to accumulate a lot of things. I'm going to send everything as bulk. If you can, then you can basically amortize this cost of doing things. Other thing is communications is excruciatingly slow. So within a memory system, it's about probably a couple of hundred plus compared to CPU communicating. In a cluster interconnect, you can do tens of thousands of instructions in the CPU by the time it get communicated. In like a grid, or if you are doing through the internet, and I mean you know, it's in the seconds now. You can actually feel it, and your processor can run billions of instructions in that time. And so if you are waiting for something, okay, you have to wait for a very long time. They might not have enough thing to stuff in the middle to kind of amortize the cost. And then you have to worry about that. So what that means is if you start waiting for something to happen, you're waiting for a long time. So you have to figure out putting things in there, not waiting. This non-blocking things is very important because of that. And so normally what you want to do is you want to have always split operations. That means you want to kind of initiate something at some point very early on and then use it later, especially if I'm looking for something like a receive. So if I want to, especially if I want to get some normal in the shared memory, just kind of doing a simple thing, asking something and get reply is very simple. Here because if you just do that, there's a huge wait in between. So you want to kind of do split operations. So this code can be very complicated because you're trying to, if you want to ask something, you ask very early, you do a lot of other things before the reply comes. Oops. Okay, see how many times I have to press that before it realizes I didn't know how to reboot. So if you want to rendezvous with normally that means the 2 points has to kind of synchronize at the same point. So what you want to do is you can do a three-way thing. You send a request, receiver acts saying, okay, it's okay to send, and then sender delivers the data. So that means I have to do three-way communication. Or this alternative is two-way. Sender doesn't send anything. Receiver basically send a request, and then you send the data. So this could be faster because there's less things to do in here. And there's another method called RMA, or it's another name you might see is called active messages, where you don't ask the receiver. When you send, you have some pre-assigned place you can go and dump the data. So you don't wait for somebody to ask for data. You said, okay, if I want to send, I will immediately send and put it somewhere. And the data arrives and the place it here. So the first slide I showed you all that time, you saw all this big difference in the time, like things were going, either can happen, the message can go very fast or sometimes go very slow. There was a big variation here. This happened basically because of the network communications. How many of you know a little bit about TCP? Okay, so let me just explain 5 minutes of TCP before I move on. So TCP is one of the main protocols that we use to communicate over internet. And there are two things. You want to actually send data, but also you have to be a good citizen. You have to actually work in a way that it doesn't really take over the entire shared bandwidth you have. So what TCP does, it has a window. So what it says is, okay, I can send certain amount of data, that's the size of the window, but I can't move beyond that until I get some acknowledgement. So I send the window amount of data, and on the other side, when it received that data, I said, I have seen this much of the window. And once it said that this much of the window, they send that acknowledgement back. And when the acknowledgement comes, you say, aha, that's good. That means it has seen that data, I can send more. I keep sending more. And then the TCP has this very interesting property, like if we are doing a really good communication, things are going very nicely, it starts increasing the window size. So, oh, okay, that means that window size thing's going. I can do bigger and bigger and bigger window size. You can keep increasing the window size. And then what happens at some point, the system get overwhelmed, because if everybody start increasing the window size, too many packets start coming into the network. At some point, the network in the middle doesn't have enough room, it drops something. So TCP, nice thing about the network, it doesn't have to guarantee the delivery. It can just drop something. And when it dropped, what happens is the other guy is waiting for acknowledgement. So waiting for data to come, it never shows up. So then it has this in the NAC saying, I never got it. And the problem with that is, so you have nice bandwidth, and you get increasing the bandwidth, you get faster and faster and faster, and suddenly data get missed. And suddenly you have this big timeout delay, and then everybody freezes, and then get the NAC, and you restart with a smaller window and slowly pick up something like that. So because of that, there are a lot of times what happens is this packet get dropped, retransmit happens, so you have this kind of a sawtooth pattern. Things get faster and faster, go down for nothing, for little while again start again in here. So the other way of communication is called UDP. UDP says, okay, we don't have any kind of acknowledgement or something like that, I'll just send. And you, on the other hand, figures out whether you got something or not, and send information back. So the network doesn't participate in any kind of balancing act of communication, it's end-to-end. So of course, you can be a really bad citizen and say, okay, I don't care, I just keep sending huge amount of data and somebody will go overwhelmed. But what people have found is things like, for things like video, you can send UDP and kind of manage it yourself end-to-end, can get much better than trying to do this TCP in here. So the kind of thing is, even though there's not acknowledgement or there's no real attempt to make sure all the data goes, UDP sometimes can get better bandwidth, because it doesn't drop packets in here. So this is a lot of great stuff. I mean, you guys can take the networking class and learn all about the protocols and stuff like that. Really, really cool stuff in here. So some of you might actually next couple of semesters learn all about how these things work. So I'm just giving you like lot of performance-wise, these are the issues that you have to worry about when you're doing network level thing. Okay, so that's kind of talks about a little bit about small scale. And then if you want to go to next bigger scale, why do you want to go? There can be a lot more users. If you are something like Facebook or Amazon, you have a lot more users to deal with. If you are something like what's a good one which had a lot of data? Google Earth or something like that. You have a lot of data, and you have to deal with all the data, and then that's a good way to do scale up. Or you might have huge amount of processing you want to do. Like for example, one place a lot of data and processing is things like these new basically telescopes that's coming about that has arrays of hundreds of different things. So you have huge amount of data coming from the telescopes, and you have to do huge amount of processing in that. So that basically has both data and processing. And in things like web, social networks and stuff like that, you have cases where a lot of data. So here are some examples. Some things like airline reservation system is something all the airlines have to, there are millions of planes, flights, millions of seats that you have to deal with. Things like a stock trading system. that all the trace has to come there, and the prices has to get calculated, and trades has to get validated. Web page analysis, so you do some kind of global understanding of what's going on. And I'm going to talk about the three things too: scene completion and web search, which probably everybody knows. So here's this kind of dated now, kind of a web page analysis example. So what these guys were trying to do was every weekly trawl about 151 million web pages and get about a terabyte of information and analyze page statistics. So that's what they're trying to do. Come up with some idea about, okay, what is the world happening? How did the pages change last week? And try to get like a global view of that. And at this point, you have both huge amount of data and pretty large amount of computation power that you have to build a system to do that. This is where you need a larger system. Here's another very interesting system that people build. So if you have an image here, and the image has this nice background, there's unfortunate house sitting in the front. So what this says is, okay, eliminate the house, search a very large database to find similar images, and plop something in there. Okay, so okay, you can get your face with some nice actress's eyes or something like that. Just eliminate all the bad parts and get good parts put in there. And so this one, basically what they had to do was, there's about 396 gigabytes of images out there. And so you had to classify images to get in the scene detector, do color similarity, and do context matching. So computation, what you're doing is about 50 minutes doing scene matching, 20 minutes of local matching, trying to find the right matching, and 4 minutes composing there. And then you can parallelize that and reduce this time to about 5 minutes. So here's something, there's huge amount of data. You have to look at a lot of things. You do a lot of processing to figure out we get the right thing. And this, as we keep increasing these images, as we keep asking for more flexibility and more accuracy in here, things can get higher and higher. It's a really cool application that really require large data and large processing. So of course, the kind of canonical application is probably Google. So when you say search, you want to get some nice results. So what people say is there's about 2,000 processes involved in getting this query for you. It takes 200 plus terabytes of database. This is already old now. I mean, this could be even higher now. And it takes 10 to the 10 total clock cycles for everything that needs to happen for you to get your query. And you only get 1 cent for the query. So that not only you have to do it fast, you have to do a lot of processing, you have to do it very cheap. And I think one of the biggest things that Google did is figure out how to get that done fast and cheap. And that's why they're so successful. And of course you get, oh, sorry, I didn't say. So it's 1 second response time, and the cheap is 5 cents average cost, basically. You can't do, if your compute time is going to cost more than 5 cents, it's not worth it. And you have to do it there. So this is, Google spent a lot of time how to figure out how to do this cheaply. So this is already fairly dated, but Google is very secretive of what they do. So this is the closest I can figure out. They have 3 million plus processes in clusters, so 2,000 plus processes each in each cluster. What they did was they went for the cheapest thing. They built the entire system out of the cheapest plus we can get, x86 processors, the cheapest disk, fairly cheap communication, and gain reliability and redundancy through software. So each part, I mean, supposing in Google, these data centers, there's somebody who's constantly going and changing machines and changing disks because there's so much failure. But that means you have to have the software system to keep the things redundant in there. And what they have is a partition workload. All those things are nicely partitioned and distributed through Google has this nice file systems and stuff do that. And then you have to do crawling, index generation, index search, document retrieval, ad placement, all those things happen in there. Of course, other things like Microsoft and Yahoo and all those other people have systems like that. So this is kind of what, when you have to scale up, there's no other way. You have to actually build this huge system to do that. So one thing Google does, going a little bit technical, is this have a system called MapReduce. How many of you have heard of MapReduce? Okay, so there's all these people who know MapReduce, probably more than I do. So the idea there is you have a bunch of data, a huge amount of data in here. And normally what I have to do is find some similarities in a lot of data and do some processing for that. And this is a programming model set up to nicely help doing that. So that this borrows a lot of functional programming. What that means is I am not changing data. I am always taking some values and creating something new. So I'm never changing something existing. That's basically main idea about functional programming. So MapReduce has two components. First, the map. That means given some input value and a key in there, what it generate is some intermediate results and output key. So you get a bunch of values coming through, and everybody process each value separately and say, okay, so here's the output key, and here's some intermediate value. And then what you do is things with the same output key get sorted into one list. And then it's given to a reducer. And the reducer takes the output key and this list and say, okay, look, I'm going to process the entire list and down to one element or small data item. Okay, so let's go through a little bit more, digging deep into that. And so here's, in map, basically you get a huge amount of records from the data source, and it feds into this map function, and it produces an intermediate results in there, and the reduce function basically combines the data and all the for the intermediate. Let me give you an example. I think that will show you there. So here's kind of the architecture. So you have huge amount of data sources. You have many sources in here, and each of data comes into that, and the map will basically distribute it by keys and values. So there could be millions of keys values, and then what we have to do is we have to wait till all the data has done that, and then create for the number of keys here, number of reducers. So hopefully you won't have a lot of keys. If you have only 2 keys, you don't get that much parallelism, because then you'll be 2 huge lists. And then again, what happens is these keys get paired to the reducers to come to the final value in here. So what's the parallelism here? What makes the parallelism go high or not have enough parallelism? Yeah, I mean, first of all, you need to have enough, hopefully, multiple data source stores, so you get a lot of parallelism coming in there. Map is easily parallelizable, because each choosing in there. Reducer is the problematic one, because if you have too many keys, too little keys, you are in trouble. The other interesting thing in here is there's a big shuffle in between here. So that means data has to go all over the place. So it's not something that you got data and you process to the end, you got data, you process to the end. Every data has to kind of cross back, and so there's huge amount of communication in here. That could be bottleneck too. So that can be bottleneck, keys can be bottleneck. So map function runs parallel, creating different things. Reduce functions also run parallel for each key, and all values are basically processed independently because of that. And also the bottleneck is reduce phase can't start until all the map is done, and also all the data gets shuffled around that. So here's an interesting example. What I'm trying to do is I'm trying to count the number of words in assume huge amount of web pages. So what I can do is in the map, I get each page in here. I iterate through the page, emitting each word as my key and the count as 1, because I only get one thing. Okay, and then my reducer is basically my key is the word, each word. So if I have million words, I can have million reducers, and the reducer basically takes all those things. This is not that fun because everything is only have number 1 because we counted 1, and then basically keep adding up how many things for each word came about, and put up the result. So you can say, okay, look, for the entire corpus of data, I had this many words count, this many word occurrences, this many each for each word, you get a word count. So basically trying to kind of create a histogram in here, and MapReduce provides a very nice interface to do that, and it's very nice high level. And they provide this nice infrastructure to kind of run this in parallel. Yeah, in parallel in here, and do all the communication necessary. Figure out how many reducers to run, allocate machines to run them, produce the results, and give you the result. So this is a nice infrastructure Google has built in there. So in this level, when you go to this is the data center level, what do you have to do to scale? You need to distribute data. And you need to parallelize, because if all the data is in one machine, it doesn't help. And you need to have parallelism to kind of scale it here. Another interesting thing you can do is approximate. So what that means is, in a normal, when you calculate, when everybody has the same data all the time, because when you write the memory, everybody sees that memory, you have kind of the perfect knowledge of the world. And in a distributed system, getting perfect knowledge is very expensive. That means every time something changes, you have to send everybody that data. And one way that people really makes these systems run fast is say, wait a minute, if somebody doesn't have the perfect knowledge, if there's a little bit of discrepancy between something, I'm okay. If, assume you have a new, you change your, we'll say, web page, and added a couple of new words in there. Next second, the search doesn't see it. Nobody's going to complain. And you can delay that. Or if you do a search, you will find something, but somebody else doesn't do it because that data haven't propagated that to both of the things. Nobody's going to complain and say, wait a minute, I found it, but he didn't. It can have a little bit of a lag. And that can be really, really useful in this kind of system. So because you don't have to, every time something happens, you don't have to keep updating. But tell me a system that you can't actually do that. Kind of play it a little bit fast and easy. Stock trading, yeah, that's something basically, if you say, yeah, you might get it too, and that doesn't work. Basically, stock trading has this very particular thing, because minute you submit we'll say a sell order, within certain amount of time it has to get matched up and has to be announced to both people, and also there are a lot of other constraints, like, okay, if the machine goes down, okay, either trade has to be everybody saw the trade or nobody saw it. Well, you can't say somebody says I sold you and the other guy says I didn't buy it, and when you have millions or billions of dollars back and forth, that doesn't really work. So for that, there's this thing called transactions. So transactions is an interesting way. A lot of databases have this transaction. Transactions say, okay, look, I am doing this very complicated thing. Okay, and I cannot have this intermediate state going on. So what transactions say is, first tell me everything I want to do within the transaction. So it might be I want to sell a stock, I want to buy a stock, whatever. And then at some point when you commit the transaction, you either say, okay, everything worked, good, the entire thing get committed, and you are done. Or it can explicitly reject it. It can come back and say, look, okay, I can't do this transaction now, sorry, you can restart it. So you can accept and reject, but then what the nice thing about that is then every one single, it's like atomicity. Every one action doesn't have to happen immediately or happen as a group. You can say, okay, I'm doing a bunch of action in a transaction, and then finally I can commit, and if it works, great. So what might be a reason you might not be able to commit a transaction if you do a transaction? Anybody else want to answer? What might, when you say I want to transact, I want to commit something, what might say, so here's an interesting thing in the stock trading type world. So assume I want to sell something. Or let's look at the airline reservation. So assume I have an airline seat in here. And if two people want to try to reserve that seat, I can do all this processing parallelly for everybody until I come to the commit point. That means I can look at everybody, ask them to enter the data, give the price, all those things separately for the same seat. But then when you come to the commit point, you can say, okay, can I commit the transaction? At that point, only that point they have to figure out whether there's a conflict in here. And at some point, if there's a conflict, you say, oops, can't, one transaction has to get aborted. The nice thing about that is most of the time, people are not going to fight for the same seat, and then things can proceed in parallel. You don't have to wait. Otherwise, if you do that, there might be only one seat assignment at a time you can do, and that's really not going to scale. So everybody tried to get their seat. They go to the end and they say, okay, can I proceed? And at that point, you check whether there's a conflict. And there's a conflict, one guy backs out. So that's the transaction. Oops, I'm going to get rebooted, I guess. So when you go to planet scale, you can get even into more issues. Things like, what could be a planet scale thing out there? What's the interesting planet scale thing that you can think of? Single computation that has to happen at the planet scale. Something like internet naming system. It has to work everywhere in the entire planet, or something like the internet routing. There has to be a algorithm that has to work. Entire world has to cooperate and make sure that all the traffic actually goes to the right place. So there are a lot more issues, interesting things show up in here. Things like SETI at home type stuff. These are a little bit dated these days. That happens distributed all across the place. So if you do planet scale, it has to be truly distributed. Okay? There cannot be any global operations, no single bottlenecks, and you have to have distributed everywhere stale data. You cannot say like, okay, look, everybody has to have the same data. You have to have that, everything distributed. And it has to adapt to load distributions because things can keep changing in there. So what I'm going to do next is trying to give you a little bit of a case study that shows you some interesting properties that show up when you start building at that scale. And this has some planet scale type properties, some cluster properties, whatever. And I will probably first describe this interesting problem and then show what kind of solutions that came through. So to kind of give you a feel for a perspective for a problem in here. Okay? Any questions up to this far for distributed systems? It's kind of hard to do a distributed systems in one lecture. There are almost closest for distributed systems, but okay, this will give you a feel for some of it. So the case studies here is this from VMware. It's called deduplication at global space. And the problem shows up when you're trying to move virtual machines across the world. Okay, you have this virtual machine. So what virtualization did was it took a piece of hardware and it converted into a file. So each machine is now a file. Okay, when you have a file, unlike hardware, there are a lot of cool things you can do that. You can replicate those files. So suddenly instead of one machine, you've got tens of hundred machines. You can move those things in here. And of course, you can get started in other machines all over. So once you are able to move these things, the issue comes how to move those things around. And what's the cost of moving something? And also you can store those things somewhere in a database. So what you want, the interesting thing that's happening these days is cloud computing. Cloud means there's all these providers all over the place saying, okay, I have processing power, I can give you something. Amazon does something easy too, but Verizon is trying to do, everybody is trying to do that. And so if you want to have the best market, what you want to do is have the elasticity to move from cloud to cloud for many reasons. So sometimes the cloud might be too small. You want to get to a bigger cloud in there. Or you want to be near the user. So in the daytime in US, you want to probably move your machines to US. At night, there might be users might be in China. So you want to move your compute near to China because it will be closer to the people who are using it. So something like that, you can move around there. Or you want to find the cheaper provider. Somebody come and say, look, I can give you a compute power 10 cents cheaper than what you're getting. Okay. I want to move to that guy. And also the amortize the risk of catastrophic failure. If there's a hurricane approaching somewhere, I might want to move to a data center that might be out of the way, and I want to do that. And the interesting thing there is this a lot of things, but when you say machine or in application in the cloud, it's a machine. Machine basically in a virtual machine. There's an entire virtual machine has to get moved around, not your small application. The entire thing has to move around. And virtual machines are hefty because it has the operating system, it has all the software. So there's so many things other than your data and your state. There are a lot of things in the machine in here. And all those things have to get moved around. So that can be expensive. So here's an interesting experiment in here. So idea here is to try to move something from Boston to Palo Alto on a 2 megabytes network, and there are a bunch of different virtual machines in here, VMs, and it takes whatever 3,000 minutes to move these machines. So from this is 500 minutes. That means what? Yeah, some hours to more than some hours to move these machines around. And then what you can say, okay, look, the machines are heavy, big. Why can't you do the first compress the machine? So you can use something like normal compression. So blue is basically compress, move the machine, and decompress. So here's something interesting. This is a very fast compression. Okay, you did really well. You are going there. If you do even a better compression, you say, okay, I'm going to do a full best compression I can do. It's actually slower because the trouble is the compression time is so low, so high, the reduction is not usable in here. So you try to compress, you spend most of the time compressing, so actually this is even slower than just sending without compression. So compression is important, compression is useful, so can you do better than a normal compression in here? How can you do better? So some key observations in here. So large part of these files are executables. Okay, you have your Linux kernel, whatever, all those executables sitting in there. And basically, there's monoculture in the world. There are no million different executables. Okay, your Linux kernel, there's only certain amount of versions. Microsoft XP, there's certain types of versions. So even though there are millions of machines, inside the millions of machines, there are millions of different applications. There's only hundreds of different applications. And so you're if you think about it, you're moving the same thing again and again and again. Can you take advantage of that? And there's even substantial redundancy in each disk. So this is very interesting. If you have a Windows machine, each DLL has 3 copies. So you have the copy, and then you have the installer has a copy, and there's another copy in the next version to basically back out, so undo copy. So each thing is kept 3 copies, so every big thing is in multiple copies in there, so that part is there also. Even within a single disk, there's redundancy in here. And other interesting thing is, many of the disk has large amount of 0 pages. So if you send something uncompressed, you send huge amount of zeros. So you're waiting for zeros to get in there. So compression, even easy compression can get rid of zeros, but this is large chunk of data in here. And so the interesting thing is, if you take one virtual machine, this is the number of non-zero blocks, and this is the number of unique blocks. So Unix blocks are smaller than non-zero blocks. But if you keep adding more and more virtual machines, then of course the number of total blocks keep going up. But the non-zero, the unique blocks doesn't keep increasing. That means the second Linux box you add, there's not much new in there. So if you look at that, what happens is the first guy has about 80% things are unique. When you keep adding things, it's about only 30% is unique after you add, because it's the same program. Only the data is different as you keep adding. So can you really take advantage of that? So that is where deduplication come in. So deduplication says, I have this data, I have a lot of redundant data, so AB is redundant. So what you want to do is break it up to some kind of blocks in here. And then one easy way to do is calculate a hash, because you don't want to compare blocks. That's too much. N squared comparison of blocks is a lot of comparison. You can have some kind of hash calculated for each of these blocks. And then you can compare the hashes, and if the hashes are same, they are the same blocks. And then what you can do is you can eliminate most of these blocks in there, and then keep hashes for each block, only the hash. And then what you can do is you can only keep the unique blocks in here. So even though you have 9 in here, only 5 different unique blocks are there. So that's a nice way of deduplicating. So what you have is what you call recipe and a common block store in here. So one way to do that is you can have a recipe and common block store for each of the system in here. That's a traditional deduplication. Or what you can do is have everybody keep a recipe and only have one common block store. Just keep one single common block store and everybody have a recipe, or probably cache of a recipe. So by doing that, you can even reduce a huge amount of things happening in here. So the interesting thing is, if you're keeping one common block store, who can keep, who can manage? That's the interesting question in here. So can you keep, instead of a common block store for each processor, each computer, can you keep the common block store for the entire world? So you find most of the common blocks in the world, keep one store. And nice thing about that is then I can go anywhere in the world. I can ask for the common blocks for the common things. I can populate myself. Aha. So here's this interesting system called the bonsai. What they did was, so if you have a block in here, you calculate a hash function in here, get a hash key. Okay? So what that means, hash key can uniquely access this block. And then what you want to do is, after that you want to compress this block. However, there's this additional step I will explain later why it's needed. So other thing you can do is you can create a second hash key and use that as a private key to encrypt this block. Okay, so you calculate two hash keys. One is the hash key to identify, the other one is a private key to encrypt this block. And then what you can look at is this global store to see whether this hash key exists. If the hash key exists, they say, okay, I got the page, here's the page, that's an encrypt page, and I have each page will have a unique ID, and say, here's my unique ID. If you find the page in here, what you can do is you can only store UID and this private key and get rid of my page. So storing UID and private key is sufficient to get my page here and uncompress. Why do you think I have to compress here? Oh, sorry, why I have to basically do encrypt here? What's the interesting thing about encryption? Why encrypt? Especially if you assume this is global. Because if you don't encrypt, it might be a common page, but it might not be something you want everybody to know. So assume, not here, assume like a large company like Google. President of Google or Larry Page send everybody emails and this is very private, but here's something that's happening in the company. And it will get into everybody's mailbox and suddenly it becomes a common page. And it gets sucked into the world because of the common page, and now everybody can see that. And that's not good. But now if you have this private key, if you don't have the private key, I can't decrypt that. So what happens is, let me go through what you can do in here. And then what can happen is, if you have these two, UID and private key, you can go to the global storage and say, okay, here's the UID, give me the page. It has a page, you better have the page for that UID. Get the page out of that. And then now I can use my private key to decrypt it. And then of course I can decompress it on an original page. So by doing that, I can have this global system that keeps common pages in there and store them. I can basically really eliminate the storage, because nice thing is this could be, we'll say, 2K pages, and this is 64-bit, and this is probably 256-bit. So there's a huge compression you can get in there. So interesting thing so here are the kind of decisions you have to make. For example, hash key. So each page is represented by a hash key. So, but you can have two hash keys, same hash key, two pages mapping into the same hash key. So my God, you're not unique. So why is it okay? Very low probability, and in fact what they looked at was they calculated the disk failure. There's a higher failure of disk failing and losing data than a hash collision. So you can say, look, you're keeping data in the hard drive, so there can be more chance of disk failure than hash collision. So therefore, hash key is you can do that low enough probability you can get away with that. Actually, I want to skip the rest of it. This in there. So so here's the kind of comparison, how much compression you can get. Some of the time you almost can compress 100%, because if you have a newly installed Linux box with very little data, everything is in the global. So by doing that, basically here's the communication. The compression is cheap. You don't have to do too much because you just do this hash comparison to do that. And then now the communication time is even reduced because you communicate a lot less, and then you have to expand that. So all these three are actually now much faster to send a machine across. So here's the total size of all the VMs. The interesting thing is, if you compress within, just do compression. This is mainly, most of this is zero blocks. You can eliminate the zeros and do very simple compression in here. And if you do local deduplication, if you eliminate that, and if you do global, you get to this point. So you get to about basically 30% of original data. And yeah, there's more data in here. I will just and okay, so that's kind of interesting global level system that people are building today. And I think if these kind of systems appear in many different places, like things like these days a lot of people are building things like cell phone games and things like that has this huge back computation. All those things have this kind of large scale ability in there. And so the nice thing about performance engineering is, even though if your application doesn't require huge amount of computation, no very fast processing, if you're going to have millions and millions of users, or if you're expecting millions of users, then building these systems and understanding and building scalability is really important. And a lot of the things we learned in this class is kind of directly applicable there. So any other questions before you guys can go finish your project report and go have a nice Thanksgiving dinner? So everybody thinks that they will be able to get a good handle on what you're doing for the final project. But oh, come on, and there's so many cool things you can do with this project. And there are whatever 3 or 4 iPod Nanos waiting. So it makes a lot of sense to actually really focus this one. This is a fun project. This is, in fact, is a fun project because talk to these guys, what they did last year, the people did a lot of interesting things, including, because we gave you freedom to actually even change the algorithms. So you can actually look at the algorithm. I mean, if you know a little bit of physics and graphics type stuff, look at that and say, okay, look, can I even reduce computation of how the computation is being done? So people got a lot of wins by doing things like that. And of course, parallelization matters, and there are a lot of optimization possibilities in this piece of code. So take a look at that, understand, just have a plan. Just don't go blindly into it. Just have a plan, run it, profile it, get some feedback. You need to get this for your presentation. So run, profile, get some feedback, have a good plan, go attack it. Okay, so see you in a week.